Hello everyone. This video is for CVPR2020 tutorial, Image Retrieval in the Wild. Thank you for attending this session. I will introduce a large-scale visual search system in the consumer-to-consumer marketplace app, Mercari. I'm Takuma Yamaguchi, and I work in Mercari Inc. as an engineering manager for the machine learning team. I developed and integrated a visual search feature to the marketplace app. So I will talk about the project in this session. I am talking about visual search applications and services first, and then I will show how to build a scalable visual search system. During our offline evaluations of the visual search feature, we encountered one big issue related to the image representation. I will share what was the issue specifically and how we solved it. We are using the visual search techniques for other purposes in addition to the feature to search items by user-taken query photos. So lastly, I will introduce some other applications of visual search. Before getting into the main topic, let me clarify the wording visual search. There are some expressions for retrieving images, like image retrieval, image search, visual search, and so on. Image retrieval and image search are general terms for search images by metadata, keywords, tags, and images. As for visual search, reverse image search and CVPR mean search images by images. I will talk about a visual search system, so the scope is search images by images. Let me introduce some visual search applications and services first. There are some image search applications like Google Images, Bing Images, Pinterest Visual Search, and so on. Not only search images on the web and SNS, but also some e-commerce and retailer apps like Amazon and eBay provide visual search features for better user experience and better discoverability of contents and listings. In addition to such 2C features, some visual search services are available. So visual search can be integrated without developing visual search core engines using SARs and APIs like Google Cloud Vision, Bing Image Search, and Vicenze Visual Search. In the e-commerce industry, some services provide visual search features like Amazon, eBay, Alibaba, and Mercari. This picture is one frame of a promotional video for the visual search feature on the Mercari Japan app. I'm working for the Mercari Japan app and the Mercari US app. The Mercari app is a consumer-to-consumer marketplace where individuals can easily sell used items. We are running our services in Japan and the US. There are various kinds of items in the service, such as apparels for women, men, kids, electronics, games, and handmaids, and also cars and motorcycles as well. The number of monthly active users is over 16 million, and the total number of items is over 1.5 billion. So the system should be highly scalable. Also for the visual search feature, high scalability was required. There is a question. Why are many services interested in visual search? The answer is simple. We can find objects and items which are not easily discovered by text-based search. How do you query when you look for clothes like this? Plaid and shirt, plaid and blouse, checks and blouse and frill, gingham plaid and blouse and frill and collar. There are many combinations of terms and keywords, and the way of expressions depends on the users. If you find what you want, you are lucky. If not, you just get tired. Especially in a C2C marketplace, enough information for each item is not always provided because the sellers are not professionals and sometimes lazy to put sufficient information and keywords to their items. This item is in the category women tops and blouses button down shirt, and the description is black and white plaid shirt. So this item cannot be discovered by a query gingham plaid blouse, even though the query terms are correct, because the item description doesn't have the keywords gingham and blouse. When we look for clothes like this, query we may query with this kind of such terms: black, white, plaid shirt. The results look visually similar, but the sleeve length is different and no frills, so these are not what we want. Then we may change their search terms to like gingham, plaid, frill, blouse. The results look visually similar, but no colors, no buttons, so we may not be satisfied with the result. As for the visual search, these results are definitely better than the text-based search results. With color, buttons, similar texture, similar sleeve length. Is the visual search always better than the text-based search? In this example, the query was iPhone XS Max 256 gigabytes. Through the visual search, some types of iPhones were extracted, like iPhone X, 6S, 7, and XS. And also, it's impossible to recognize the storage size from images. As for the text-based search, all the retrieved items were iPhone XS Max 256 gigabytes accurately. When sellers and buyers describe products in the same way and or visual information is not enough to explain products like storage size, text-based search is totally better than visual search. So sometimes visual search is better, sometimes text-based search is better. Since this field is hot in the e-commerce world, there are many studies, articles, and statistics. I put some of them here, such as Gartner said by 2021, retailers that support visual and voice search will increase their e-commerce revenue by 30%. In another survey, many millennials want a visual search to discover products on their mobile devices. So I think more e-commerce and retailer apps will have visual search features in the future. Let's move on to the next topic, visual search system. For experiments and POC, the system architecture would be like this. The components are image feature extraction, feature vector storage, and similarity search engine. In the index phase, images are transformed into feature vectors and they are stored in the storage. In the search phase, a query image is transformed into a feature vector and top case similar vectors are retrieved, comparing the query feature vector and the database feature vectors. Practically, a similarity search library or algorithm should be used. There are many options like Phase, NMSlib, Annoy, and so on. I usually use Phase because GPU implementation is available, some similarity search algorithms are implemented, and the software license type is MIT. This architecture is just for experiments and POC. So after you confirm the visual search performance is high enough for your applications, the production system will be discussed. The architecture would be like this. To receive requests from clients and return results to the clients, API servers are needed. And for each component, multiple servers should be running to keep the system always available. All the servers should be monitored. Unhealthy servers should be replaced with new ones. And when the system load becomes high, the number of servers should be increased, and/or more computational resources should be allocated. In large-scale services, many servers are running, so some servers can get unhealthy all the time, and system load can be suddenly increased. It's troublesome. Even though the visual search performance is wonderful, the cool search experiences cannot be offered without system stability. To improve the stability, the first step is to Dockerize each component. Docker makes your development, test, and deployment safe and efficient. It's helpful and useful, but not enough to keep the system available efficiently. The next step is to use a container orchestration system. Kubernetes is the most popular one, and it's available in the major cloud services like GCP, AWS, and Azure. It's an OSS, so it can run on on-premise environments as well. It provides self-healing, auto-scaling, resource management, and so on. The system operation cost can be drastically reduced. I want to talk about how to update the search index next. Let me simplify the picture. The components are the same as the previous slide. They are Visual Search API service, Image Feature Extraction service, and Similarity Search service. Visual Search API service receives a query image. Feature Extraction service returns a feature vector representation of the query image. Similarity Search service retrieves similar vectors to the query vector. And the Visual Search API service returns the result. On Kubernetes, a pod is the smallest unit, which consists of one or more containers, like a feature extraction container and a logging agent container. A service is an abstraction which defines a group of pods. We can update the search index periodically with our batch processing. Image feature vectors are extracted from newly posted images, and our new similarity search index is built for the new images and existing ones. Then a new Docker image which contains the new search index is built, and it's uploaded to the Docker image registry. Such a registry is available in the major cloud services. When the Docker image is updated, the image is deployed automatically to the Kubernetes cluster. If the search index doesn't have to be updated real time, this system would be practical enough to handle up to 10 million images. In Mercari, hourly index update is acceptable, but the index size is not 10 million. At least hundreds of millions of images have to be handled in the system. So we divided the index into multiple ones: monthly, daily, hourly indexes. Every hour, a new hourly index is created and deployed. Once a day, a new daily index is created through merging the hourly indexes. Once a month, a new monthly index is created through merging the daily indexes. Similarity searches are executed in all the similarity search services, and the results are merged and sorted by similarity scores. If the feature extraction model is small enough to run on mobile devices, you could reduce the latency and network traffic. In the Mercari app, the feature extraction model runs on the server side currently because it's easier to replace the models and do experiments for some feature extraction models. Since we have a plan to put the model on the client app, we use MobileNet. After we make sure that the model is stable enough and performs well, it will run on the client app. After the update, the client app will send feature vectors rather than query images. This is an overview of the visual search system in the Mercari app. Since item images are in AWS S3 and our services are running on GCP mainly, we use the both cloud services, AWS and GCP. In the both cloud services, we use Kubernetes. Search indexes and Docker images are created in the Kubernetes cluster in AWS, and they are deployed to the Kubernetes cluster in GCP. Let me introduce details of similarity search. Exhaustive search is not practical for this purpose. We use IVF ADC through our similarity search library phase with these settings. In this experiment, we assumed covering 1 year items, and for each monthly, daily, hourly service has 30 million items, 1 million items, and 100,000 items, respectively. The numbers are different from the actual ones. One item has one image in this case, so 362.4 million image feature vectors are stored in this experiment in total. The similarity searches are performed parallelly. When we allocated 4 CPU cores for each service, the processing times were 20 milliseconds for monthly index, 13 milliseconds for daily index, and 12 milliseconds for hourly index. The number of images and items are totally different between the indexes. Practically, computational resource allocation and similarity search settings should be optimized for each similarity service. Docker allows us to allocate resources flexibly, like 1.5 CPU cores. For the feature extraction, 62 milliseconds is needed. Object detection model is also running for the visual search. It takes 168 milliseconds. So on average, 255 milliseconds for one request is needed. Actually, our production system is more complicated than this. For example, the system should return the whole item information like item title, description, category, brand, price, and so on. So after the visual search, the system access to an item database to get such information. This looks complex. Can we simplify the system architecture? As I mentioned earlier, the feature extraction model can run on the client side. And also, the object detection is able to be placed at the client side. If the similarity search services and the indexing pipeline can be simplified, the whole system architecture can be simple. One option is using Elasticsearch. Elasticsearch is originally a full text search engine. The open distro enables similarity search on Elasticsearch. Internally, NMSlib is used. If the memory consumption is acceptable, because NMSlib, HNSW stores the original vectors in the index, and if you are familiar with Elasticsearch, it may be an option to realize a simpler visual search system. For efficient similarity search, a batch indexing is recommended, also for here. I left my notes as blog posts when I tried to use Elasticsearch for the similarity search purpose. If you are interested in them, please take a look. When I developed the image feature extractor for the visual search system, I encountered a C2C marketplace specific issue. I will share the issue and how I mitigated it. The model for the feature extraction is MobileNet v2. The model was trained with a classification problem setting. The class labels were combinations of category, brand, and texture, like Nike striped men's golf polos, floral girls' dresses, Louis Vuitton women's long wallets, something like that. The dataset was created using 9 million images from their marketplace Mercari. The feature vector dimension is 1792. Then in our POC, using 100 million item images, for these kinds of query images, the results seemed acceptable and practical. Then the query images were worn apparel by models. The results tended to be worn apparels as well. The results are very visually similar. so in general, it can be acceptable. However, in Mercari, it's not acceptable. Before moving on to the details, let me clarify the wordings. For apparels worn by models, I describe them as fitted apparels. For apparels laid flat on a surface or hung on hangers, I describe them as flat apparels. The problem was Mercari is a C2C marketplace where most sellers and buyers are not professional people. So most of apparel items are not worn by models. Most of apparels are laid flat on a surface or hung on hangers. When a query image is a fitted apparels tend to be retrieved more, even though such items have a very small proportion in the marketplace. It's the problem. Another problem is that showing many items listed by professional sellers can cause problems for the C2C marketplace. For example, hurting buyer experience and discouraging non-professional sellers from listing items. So we wanted to show these results for this kind of query image rather than this. To mitigate the problem, we transform the feature vector with this manner. The idea is subtracting human features from the original vector. Here, the small f is a function which extracts a feature vector which has no negative value elements and whose L2 norm is 1. And the capital F represents a human feature vector. I will show you how to generate this later. For feature vector of fitted apparel, a similar feature vector to our flat apparel is generated by subtracting the human feature vector from the original vector. Since the original feature vector doesn't have negative value elements, negative value elements are replaced with 0 after the subtraction. And the L2 norm of the original vector is 1. L2 norm normalization is also performed so that the scales of the left side and the right side are the same. For feature vector of flat apparel, the original vector is preserved even though the same human vector subtraction is performed. Thanks to this characteristic, the feature transformation can be applied to any kinds of images, no matter whether the input image is apparel or non-apparel, fitted or flat. Without this characteristic, we may need to have an additional classifier which classifies whether an image contains fitted apparel or not. This is still a heuristic, but it works for us. Originally, the feature vector has no negative elements thanks to the ReLU. So we just added L2 norm normalization after the global average pooling. Regarding the human vector capital F, it was generated by this way. For some apparel categories like tops, dresses, and bottoms, difference vectors between fitted apparels and flat apparels were calculated. The T1 represents a human vector of tops. The vector is calculated by subtracting a median vector of flat tops from our median vector of fitted tops. The TC represents a human vector of bottoms. The average vector of these difference vectors is their human vector. Here are the experiment results. In this experiment, a retrieved item was evaluated as correctly selected only when it was an image of flat apparel in the same category as the query image. For the fitted apparel query images, the results were significantly improved. Originally, for the flat apparel query images, the results were not bad. Interestingly, using the feature vector transformation, the performance was better in the most cases. So the transformation seems to also remove some noise features as well as human features. In other words, the feature transformation may extract essential features. These are the qualitative experiment results. For these fitted apparel query images, with the feature transformation, flat apparels were retrieved successfully. Without the feature transformation, mostly fitted apparels were retrieved. We also used some images from another dataset, which is ETL dataset, as the query images to show the feature transformation generality. And the results looked good as well. In the marketplace, not only apparels, but also many other categories are there, like toys and bags. So it's important to show there is no negative impact by the feature transformation in non-apparel categories. For non-apparel query images, as we can see, no serious negative effects were given by the feature transformation. These results are not exactly the same, but very similar and look practical. So this comparison indicates that the feature transformation can preserve the essential image features. The last content is applications of visual search. A visual search system can be used for some other purposes, in addition to the feature search items by user taking images. This is the demo video for the visual search feature. For this query image, Amazon Echo Dots were retrieved. And for this, Louis Vuitton wallets were extracted successfully. More features and applications can be realized using the system, such as find similar items to a sold item, item information prediction for sellers, price estimation by image, item monitoring, and prohibited item detection, and so on. Let me introduce some of them. Find similar items to a sold item. This is a straightforward use case of the visual search. Users who visit sold items can search visually similar items to their sold item without taking a photo. For the both cases, describing the texture is not simple and consistent among users. Visual search may bring better user experience. Next is not an item retrieval feature. It's image recognition. In Mercari, the visual search feature is available only in Mercari Japan app, but this feature is available in both the Mercari Japan and the Mercari US apps. When a seller lists an item, the item photos are taken first. Then item category, brand, and title are filled automatically by an image recognition. In this case, title was Amazon Echo Dot third generation. The category was smart speakers and assistants, and brand was Amazon. These were recognized correctly. Actually, the image recognition feature is running on the similar visual search system. When the item images are sent to the system, visually similar items are extracted. And the item information and of the similar items are compiled with a majority voting manner. Then generated title, category, and brand are returned to the client. Let me conclude my presentation. If you are thinking about integrating visual search feature into your services, I would recommend these processes. Try some visual search services first. Developing a visual search system is fun, though. If you find a service which meets your expectations, use it. Even if the pricing is an issue, use such a service first. Then confirm if the feature is useful for your service. If necessary, consider developing your visual search system on your own for performance improvement and cost reduction. If you need a highly scalable and flexible system, build it on your own. The cost for developing and operating a visual search system would be high, so be aware of it. That's all. Have fun with visual search system development, and I hope my presentation will help you. Thank you very much.